our next speakers. All right, it's my pleasure to introduce our next two students. They are civil engineering students, and the project we're going to present is an environmental engineering project for two guys. Done an exceptional job, very impressed with completed. So on the left we have Lauren Miles, and around Shelby.
Thank you, Dr. Bill. I'm Lauren, this is Shelby, and our project is an evaluation of dewatering alternatives and a preliminary design for the Evansville Water Treatment Plant. Evansville Water Treatment Plant is located in downtown Evansville, and on average treats 25 million gallons of water per day. It has the capacity to treat up to 50 million gallons per day. The plant delivers water to approximately 60,000 customers over Evansville. Currently, the plant has no dewatering facilities to handle the continuous discharge of sludge from its primary clarifiers and filter backwash cycles. This is a process train of the current treatment process at the Evansville Water Treatment Plant. You can see over on your left, the water enters from intake building from the Ohio River, and here is a potassium permanganate and water activated carbon before either going to the north or south primary clarifier, where coagulation and flocculation sedimentation take place after allocoagulant is added. After primary clarifier, the water goes to either the north or south secondary clarifier, and then disinfection takes place before filtration through multimedia filters. The water then goes to a clear well and a pumping station out to the distribution grid. You can also see that there are 3 different waste streams that are directly discharged into the Ohio River. This is an aerial picture of the plant. You can see here is the south clarifiers, this is the north clarifiers, and the filter buildings. The green arrows show where each of the 3 waste streams discharge into the river. And right now, the plant produces in excess of 20,000 pounds per day that goes directly into the river. The National Pollutant Discharge Elimination System, along with the EPA's Clean Water Act, restricts solids put into the river. They have a permit right now that will run out within the next 2 years. It is expired upon reapplication that a dewatering facility will be necessary. The objective of this project was to evaluate possible dewatering options in anticipation of increased regulatory constraints. You can see on the map, this is our proposed location of the new dewatering system. The north side of the plant was also considered, but will not be possible as there's a clear well underground there.
Okay, so we took some samples from all 3 waste streams, and this is just a picture of what is going into the Ohio River each day. We did some laboratory testing to find properties of all 3 waste streams. Tests we ran were total solids, total suspended solids, and a percent solids test. We found that the percent solids for all 3 waste streams were very low, less than 0.5%. This is an area of concern because mechanical dewatering equipment requires the percent solids concentration to be at least 0.5%. And as you can see, we're well under that. Also, total suspended solids is an area of concern because it's a very low concentration. And mechanical dewatering equipment will eliminate the total suspended solids, but right now they're just too low. So between these 2 tests, some form of thickening will be required. 4 basic steps of the dewatering process include thickening, conditioning, mechanical dewatering, and residual disposal. Thickening is a process that increases the solids content of the sludge. Conditioning is a process of improving physical properties of sludge through the addition of polymers. Mechanical dewatering is a mechanical process intended to remove free water from the sludge. And residual disposal is a reuse or disposal of solids through landfilling or fill materials. In order to gain a better understanding of the dewatering process, we decided to take a trip to Bedford, Indiana's water treatment plant. This was recommended to us by IDEM. The plant treats 3 million gallons of water per day, whereas the Evansville plant treats 25 million gallons per day. They have a 300,000 gallon sludge holding tank, which also acts as a gravity thickener to thicken their sludge. They use a continuous belt filter press as their mechanical dewatering equipment. And once the belt filter press dewaters the sludge, it is moved up the conveyor belt and loaded into trucks, and the water that is dewatered from the solids is taken to the sand sanitary sewer, where it's then pumped to the Bedford, Indiana's wastewater treatment plant. During the summer months, they're able to dewater able to produce 5 tons of solids per hour. Here's our proposed process train. We're proposing running 2 lines from the current treatment process to the equalization basin, and from here to 2 gravity thickeners, where it will then be pumped up to the dewatering facility, where our mechanical dewatering equipment will be housed, and from there, the sludge cake will be transported to final disposal site. We have an emergency overflow running straight to the Ohio River in case the equalization basin were to overflow for some reason, and we also, the decanted water and the water removed from the dewatering equipment will be sent to the sanitary sewer and taken to the wastewater plant here in Evansville.
Because there's 3 different waste streams that are all supposed to clean and have different flow rates leaving the plant, an equalization basin is needed to stabilize flow for smaller components downstream. Our design is a 100-foot by 140-foot rectangular equalization basin. It's 15 foot deep, and it'll have 2 compartments, one for extra storage. The maximum operational volume of the equalization basin will be 1.55 million gallons. Here's some flow information on the equalization basin. The purple and blue are primary sludge from the north and south primary clarifiers. You can see that they are constant throughout the day, the flow leaving the plant. This black here, this up and down, is a filter backwash flow leaving the plant. You can see that it's a constant underflow except during backwash cycles, which last half hour each. This system was developed to have 10 filter backwashes per day, and this red line here is going to be the outflow from the equalization basin. This was also designed with the assumption that the dewatering equipment will only be operational for 12 hours per day. You can see that for the first 12 hours, the outflow is 0, and then it peaks up for the rest of the day. These dotted lines here are the water level in both the compartments. This green is the compartment 1 of the primary compartment. You can see that in the compartment 2 in yellow is only used for part of the day, 12 hours. Because the percent solid is so low, we're going to have to use thickening to produce a thicker sludge. So gravity thickener is used to thicken sludge through gravity settling of solids and decanting of water through built-in meters. 2 circular gravity thickeners were designed for this system. They're 45-foot diameter and designed with a max loading rate of 20 kilograms per meter squared per day. And a typical operation level is 10 to 15 feet. This is a schematic of a typical gravity thickener. You can see in the green arrow will be inflow from the equalization basin, and the solids will settle to the bottom where a vapor arm scrapes it out, and they will come through here to the mechanical dewatering equipment. This will be the extra clear water that will flow through the pure flow through to the sanitary sewer and onto the wastewater treatment plant. To simulate the thickening process, we actually mix the 3 waste streams in proportion to what they should be leaving the equalization basin and place them in MOP cones. And basically, it's to simulate the process of thickening, which means it went from 0.15% to 1.5% solids after thickening for several hours. Conditioning is a key step in mechanical dewatering. Polymers added to the sludge entering the dewatering equipment to allow for easier solid separation from water. We investigated one type of polymer from Ashland Chemical. It was Prestol K110 LTR flocculate. This is a possibility, but there are also other companies that can also be researched.
So we researched 4 different pieces of mechanical dewatering equipment. One was a gravity belt thickener. It allows for continuous operation as well as high loading rates. It uses only gravity and 4 strands built to allow the water to be removed from the sludge. And it typically has a 0.5% to 1% suspended solids coming into the belt thickener, and it produces a solids cake yield of 10 to 12%. The belt filter press also has a 4 stranded belt, but the belt filter press sandwiches the sludge between two belts of medium and high intensity pressure. And it requires a sludge mix of 1 to 4% solids and produces a sludge cake of 12 to 35% solids. Centrifuge. It also allows for high loading rates and accepts a sludge mix of 1 to 6% solids. It rotates the liquid at high speeds to increase the gravitational forces applied to the sludge. The solids are spun to the outside of the bowl where they are scraped out by a screw conveyor. This produces a sludge cake of 12 to 25% solids, and the plate and frame filter press achieves dewatering by forcing water from the sludge under high pressure. Filter cloths are mounted on the face of each plate, and the frames are pressed together, and the sludge is pumped into the press through feed holes in the filter plates. And the sludge is fed for 20 to 30 minutes until the entire frame is full of cake, and the pressure is applied, and the liquid is forced through the filter cloth and plate outlet. The plates are separated, and the sludge is dropped onto a hopper for storage for removal. It produces a sludge cake of 30 to 40% solids content. Here's a table of some advantages and disadvantages of all 4 pieces of equipment. Some key things to note are that although the plate and frame filter press produces the highest cake yield, it also produces a higher operating and maintenance cost. Also, the centrifuge and belt filter press produce similar cake yield, 12 to 35%, and they also require similar amounts of polymer usage, but the centrifuge can handle higher loading rates, but it also requires highest energy costs. Gravity belt thickener was the most expensive alternative in our present worth analysis, but it also produces the lowest cake yield. So here's our present worth analysis that we did over a 10-year lifetime at 6% annual interest. The capital costs, or as you can see, the plate frame filter press is over $2 million, cheaper than any of the other alternatives. The analysis, the capital costs were obtained through contact with many other company representatives, and the operating and maintenance costs were found through research papers that were done from other companies that did similar design. Disposal costs and polymer costs were done for a yearly basis, and the disposal costs were based on the sludge cake yield that each machine can produce. We need multiple machines because if one machine is to go down for repairs or maintenance or some other reason, then we have another machine on backup so that the dewatering facility can still be operational.
So some typical disposal alternatives are landfilling is one of the most common disposal methods. Soil amendments are usually used with lime sludges. Hasn't been determined the benefits of alum sludges. Co-disposal is another possibility, which involves mixing water treatment plant residuals with wastewater treatment sludges, followed by disposal or reuse. And then the sludges may also be able to be reused as fill material for certain construction projects. So in addition to what we've covered here, a mechanical dewatering facility will need to be designed for this system to operate. And should be a 2-story building with the dewatering equipment located on the top floor. The bottom floor should be truck accessible for loading of sludge cake. And water removed from the sludge will be sent to the Evansville wastewater treatment plant through sanitary sewer. It is also ideal for hoppers to be placed underneath dewatering equipment for storage in between loading into trucks. It's also recommended that grading be placed underneath the hoppers in case of spillage of solids or water, and should be tied into the sanitary sewer to also go to the wastewater plant. And loading and storage area should also be on the bottom floor to allow for easy access and loading and removal of polymer containers that will be necessary for the process.
So our final cost analysis for our recommendation includes one equalization basin, 2 gravity thickeners, and 2 plate frame filter presses. Total capital cost came to be about $2.69 million, and our annual costs included operating and maintenance costs of the plate and frame filter press, as well as the polymer usage and the solid disposal at 28 tons per day, and we're estimating that to be around $414,000 a year. Here's our proposed layout for the dewatering system. The equalization basin and gravity thickeners are all drawn to scale here. And the piping network connecting the north and south clarifiers and the filter backwash system are all shown. And based on the elevation, gravity flow can be used for almost all of the pipes shown in green. So a few things left to do to complete this project are a pumping station needs to be designed to pump the sludge up to the top of the dewatering facility. Other polymers need to be researched to determine the most effective polymer for our type of sludge. A mechanical dewatering facility also needs to be designed to house the mechanical dewatering equipment, and a solids disposal method needs to be finalized. A contract needs to be done with the trucking company to transport these solids to the final disposal site. And also, alum recovery methods should be researched to determine if the alum can be recovered and used for coagulation in the plant. So a few people we'd like to thank Dr. Hill for providing us with all the help he did throughout this thing. It wouldn't have been possible without him. Mr. Tim Hall for providing the project to us and the information that we needed. Dr. Hall, Dr. McDonald, and Dr. Mitchell for sitting in on our preliminary presentations and giving us positive feedback. And Donna and all the faculty and staff for always being there to help us whenever we needed it. Questions?
All right, questions?
So, you have the outlet of the water that you dewatered, the solids are dewatered, the water that's dewatered is, you have that feeding back into the sanitary sewer. Why doesn't that just go right back into the stream where you took it out?
Well, that would be because it's basically trying to limit what you put back into the river, which is like the main thing of the project is to limit what goes back into the river.
But not back into the water, because, so you take the water out of the river, and then you settle out all this stuff.
Yeah.
And you pump out all the stuff that's settled out. And at that point, the rest of it goes towards our water fountain, through multiple processes. But then you take this stuff out, you settle out more solids. You can't put them back in the river, even though they just came out of the river. And then why don't you put the water that you got out of there back into the stream where you took it out to go through the rest of the treatment process towards the water fountains?
Okay.
I just wonder why throw it
There are,
down
like-
the sewer at this point?
You won't be able to get all of the solids out. There's literally like solids in the water. Like the whole thing is to not put any solids back in. And then any water that you put back into the river, you are with the filter back off rule, you're only allowed to recycle 10% of the water that you actually dewater. So if you put it back into the river right there, it will be run through the plant again, and that's like against the filter back off rule. That make sense?
Okay, so it's regulations.
There's a
on how-
regulation on the water you can use after you dewater it. You can only put 10% back into the plant, whereas if you just dispose it back into the river, it would just come back through. From where we have the dewatering system on the south, it would go in on the south side of the plant.
Yeah, no, I wasn't gonna put it back in the river. I was gonna put it back into the treatment plant.
Oh, that's what it is. There's a 10%
Okay.
limit, and within cost for piping to like actually put it back to the head of the plant would be over what it would cost to just send it to the wastewater plant
You have to pump it back to the head too.
with pumping and stuff.
Okay, so location and regulation.
Yeah.
Okay, thank you.
Very good presentation, guys. I'm speaking from my ignorance, this is not my area of expertise, but there are a couple of things that came up that really made me curious. Is this sludge cake, is that toxic in any way, or is it a hazardous waste?
It just came out of the Ohio River.
I mean, it's not hazardous,
So
but like,
it's the solids coming out of the Ohio River?
it's not hazardous, but not like positive,
Not
like,
obviously hazardous.
that would have to be with the further disposal,
Yeah.
looking into regulations of how much you can actually dispose in a landfill or reuse as fill material.
Okay. You mentioned 28 tons per day. And what's the volume of that? What's the physical volume? Maybe you have an estimate of how do they truck it to the landfill? primarily, that's the component.
We got a price for the landfill and that's $25 a ton, so 28 tons per day.
Okay.
That depends on your percent K yield from
Yeah.
the different alternatives, because some will have more water still left in it, and can't get all the water out of the cells, so that contributes to the weight.
Right. Okay, very good. Thank you.
Other questions? I've got one more. Can you go back to the slide with the three beakers with the water that you're putting back in into the river? Currently?
That's it.
Roughly what, I guess I should ask for this in the driver, but it would have been neat to have another beaker there with just river water, what it looks like normally. And I know you've both gone through some extensive lab experiments making that drinkable. What does the normal river water look like? I'd say in reference to the filter backwash, your clearest sample there. Is the river water, when you pull it out in a beaker, is it clear?
It depends on what day. It would depend on if we had a heavy rainfall before and where you get your sample from, but it probably, like on a normal day, will probably look pretty close to that color, like the backwash. It wouldn't be, and then if it rained for a long time, it could have a high humidity, and it would be closer to the actual primary clarified sludge.
Okay.
Does that answer your question?
Yep, so, I mean, just for folks in the room, I mean, if you went out there to the river, it would not be a clear beaker
No, it
of
wouldn't.
water that you would pull out of the river.
That's why they have a point.
Yep. All right, any other questions? All right, let's give them a hand.